In the last unit of this lecture, we are gonna talk about some fundamental machine learning basics. Most of you will probably have heard a machine learning lecture before, and therefore these basics are a recap for you. But if things are going too quickly for you, I recommend you to have a look at the chapter 5 in the deep learning book from Goodfellow et al., which describes the material that we cover here in preparation for the actual deep learning class that follows from the next lecture on in more detail. Let's start by having a look at the different learning problems. There's various categorizations of learning problems, but here for this lecture, we're going to categorize into supervised, unsupervised, self-supervised, and reinforcement learning problems. And they all differ depending on the data that is used or the supervision that is provided. For example, in the case of supervised learning, we learn the model parameters using a dataset of data label pairs. X is input, Y is output, and we have n such pairs. Examples for supervised learning include classification, regression, or structure prediction problems. In unsupervised learning, we learn the parameters of a model using a dataset without labels. It's just a dataset of inputs X here. Examples include clustering, like the k-means algorithm, dimensionality reduction, or generative models, which we'll discuss towards the end of this lecture. In self-supervised learning, we learn the model parameters using a dataset that is made out of data pairs. So we have X and X prime pairs, and such pairs in the dataset. Examples for this include self-supervised stereo and optical flow estimation or contrastive learning. And finally, in reinforcement learning, we learn a model using active exploration from sparse rewards instead of a fixed dataset. So we have an agent interacting with an environment. Examples include deep Q learning, gradient policy, and actor critique. In this lecture, we'll cover the first three learning problems. So let's start with the supervised learning problem. And in particular, let's have a look at the distinction between classification, regression, and structure prediction. In classification, the goal is to predict using a function f from an input x a discrete class label. In regression, we are interested in predicting from an arbitrary input x a continuous variable. So the inputs here can be any kind of objects, any kind of complex continuous or discrete or mixed continuous discrete objects. For instance, images, text, audio, sequence of amino acids, etc. The output is either a discrete or real number. It's important that it's a single number. So we are predicting a single discrete or real number. For instance, the label of an image. Is it the image showing a dog or a cat? Or regressing a single number for the stock market, etc. In structured output learning, both the input and the output are structured objects. So again, the inputs can be any kind of objects, but also the outputs here can be any kind of complex structured objects, such as images, text, parse trees, folds of proteins, computer programs, etc. So the difference between these here is really that in the top part, classification or regression, we denote problems where we predict a one-dimensional quantity, and here we predict a high-dimensional quantity. Today, we'll focus on the regression problem. So here's a more visual analysis of this, or overview over this different classification, regression, structured output learning problems. This is a very general image of a machine learning model F that has some parameters W, and that takes an input X and predicts an output Y. And there's two main tasks associated or interesting to us machine learners. One is the learning task, which entails estimating the parameters W from a training set of X and Y pairs in the supervised learning case. And remember that in the supervised learning case, we have a data set of X, Y pairs. And the second task is the inference task. Now, given this W, this is fixed now after the training or the learning stage, we want to make novel predictions using this model here. So for a novel X, we want to execute that function given the fixed W that we have learned and predict a Y for this novel X. So let's look at some concrete examples. Here we have an example for classification. This is image classification. The input in this case is an image. So it's out of the space of R to the power of W times H for width and height. And the model maps this to, in this case, a binary variable, either beach or no beach. So this outcome can take two different labels. Here's an example for a regression problem, which we are going to discuss in this lecture. In this case, it's an example for a stock value prediction. The input is, in this case, a sequence or a number of stock values, R to the power of n. So we have n such numbers here. And the output is a single number. For instance, the value of the stock tomorrow. And this is a continuous number. So this is why this is a regression problem. And here are some examples for structure prediction problems, which we're also going to discuss in this lecture, but in later lectures. So in this case, the input is an audio signal and the output is a sentence. So it's a sequence of words, and each of these words here is from this set of words or labels. So we have L different words in the output domain here. Here's an example for semantic segmentation, where the input is an image and the output is a label map. So for each pixel in this image, this input image, we want to determine what is the semantic class label: background, can, monkey, etc. And here's another structure prediction problem. In this case, this is 3D reconstruction. The input is a set of images and the output is a 3D reconstruction, which, for instance, can be specified by specifying the volume in terms of a voxelized grid, where for each of these voxels we determine if the voxel is empty or occupied. And we have m to the power of 3 such voxels because we have 3 dimensions, and if we assume that we have m voxels in each dimension, we have m to the power of 3. Now suppose we want to predict a output that is 32 to the power of 3 dimensional, so it has 32 to the power of 3 voxels, which is actually quite small resolution. And assume we have a binary variable per voxel, as here, which indicates occupied or free space. How many different reconstructions are possible? How many different reconstructions could the model ever predict? Now, we have binary variables here, so we have 2 to the power of 32 to the power of 3, which is an insanely large number. It's an extremely large number. And if we compare this number to the atoms in the universe, which is also extremely large, we see that this number is even larger. So there's absolutely no hope that we can enumerate all possible reconstructions. But we need to go with a more structured approach to finding a reasonable reconstruction out of this impossibly large, intractably large space of all possible reconstructions. But now let's go back to the regression problem, and let's look at what is called linear regression. In linear regression, we want to make a prediction for the model parameters in a linear sense. What does that mean? Let X denote a dataset of size n, and let X, Y be such elements from that dataset X, where the input can be high dimensional and the output is one-dimensional. So Y is a one-dimensional variable. The goal is to predict Y for a previously unseen input X. So here's an example. Here we have the ground truth of the model and some noisy observations. So these are samples from this model with added noise. This is what we provide to the learning algorithm. Now we want to learn a model such that when we execute that model at a novel location X, we get a sensible response Y. How can we do that? Well, we define an arrow function. An arrow function E measures the displacement along the Y dimension, for instance here, these little red lines, between the data points in green and the model predictions, in this case in red. And the model is specified by the parameters W. So these are basically the errors that the model makes, and we want to minimize the overall error, so the sum of all errors. In the case of linear regression, we choose a linear model for that function. So here we have this function represented as a linear model. This is just the inner product between a weight vector W and the input features X. Right? And the arrow function is simply the sum over all data points of the square of the difference in the Y direction between the prediction of the model F and the observation Y. And this little I indexes the element in the data set. And so here we sum up all these small red lines. We can rewrite this as such here because we can simply plug in this definition of this linear equation here. And what we did here is we transposed this term, right? If we apply the transpose to this expression here on the right-hand side, we get X transpose W. So this doesn't change the result because the result of this inner product is a scalar. Right? And we have plugged in here not the generic X, but the actual element in the data set, because this is the sum over all elements of pairs X and Y. Right? We have this data set of pairs X and Y. Why did we make this transposition here? Well, with that we can write this expression here more elegantly using linear algebra. So we can simply write this expression here as the L2 norm of a matrix X times this weight vector W minus a vector Y. And this matrix X here comprises all these data points, these features X here, as row vectors. W is the same, and Y is simply a vector that comprises all elements of the data set in terms of Y. So all the Y's in the data set. It's basically just stacking row-wise these X's and Y's into a linear system. And then if we compute the L2 norm here, the squared L2 norm actually, then we obtain exactly this expression, right? Because the L2 norm sums the squares of each element here. So here on the right, we already see an example. This is actually already the fit. This is after optimizing this energy function. This is the best error that we can obtain. You can see that it's not zero because these data points that are sampled from the true model in green are noisy. So we don't obtain back the true model. We just obtain an estimate of the model. And we have, in this case, a very simple linear regression model that has just a one-dimensional input and a one-dimensional output. So if we want to rewrite this in terms of this expression here, we can simply choose x, this x here, as 1 and x. So this boldface here always denotes a vector or matrices in my slides, and non-boldface characters denote, or symbols denote, typically scalars. So these x are not the same variables. This is a vector and this is a scalar. So the input here is, or this should actually be a scalar x. So the input here is a scalar x, but the vector x is then composed of 1 and this scalar. And the function is then w0 times 1 plus w1 times x, just executing this inner product here. And this is the familiar form of the linear model. This is what was used here. So how did we obtain this minimizer of this energy function E? Well, in order to obtain a minimizer, we need to follow the gradient. We need to get the gradient to 0, because we know that when we get the gradient to 0, we obtain either a maximum or a minimum, or a saddle point, depending on the function. That cannot happen here because we have a quadratic function. So what we do here is we compute the gradient, this is the symbol for the gradient, of this energy function with respect to the parameters w. So I'm just plugging in here now this linear system from before, which, if I write it out, is simply the product between xw minus y transpose and xw minus y. Now, writing out this multiplication here, we obtain this expression here, right? So we have w transpose xw. This is this, multiplied this with this. Then we have 2 times the cross term xw y, and then we have y squared, or y transpose y. And now computing the gradient of this expression, the gradient is a linear operator, so it moves through these brackets here. The gradient of the first term is simply 2x transpose xw, right? Because it's a gradient with respect to w, and we have this w here twice. So this is what remains. Here we have a linear term in terms of w, so the w simply vanishes and x transpose y remains. And for the last term, there is no dependency with respect to w, so this term is simply 0 if we compute the gradient with respect to w. So this is what the gradient of the arrow function, this is the arrow function here, with respect to w looks like. As this arrow function here is quadratic and convex in w, its minimizer with respect to w is given in closed form. This is simply a parabola, in other words. That means we can set this expression here to 0 and obtain a closed form solution. Setting this to 0, we see that the 2 vanishes, and we can put this on the other side and then divide by this expression here. So we get x transpose x inverse times x transpose times y. And this matrix here is often also called the Moore-Penrose inverse, or the pseudo-inverse, because it allows us to compute the inverse of a non-square matrix, which is the minimizer of this least square problem. So let's look at some line fitting examples now. So this is the line fitting example from before, right? We have the ground truth here in green, the noisy observations in these green dots, and the linear fit. This is the linear least squares fit of this model to the data points. We can also look at what this arrow function E actually looks like. So here I've plotted the arrow function with respect to the parameters w1. You can see that, as expected, this is a parabola. This is a squared function, a square function. Right? This is evident by looking at this equation here, which is a square equation with respect to the parameter w. Okay, so let's look at what else we can do with this simple linear least squares model. It might sound that linear least squares allows us to only fit linear models of the data, but that's not true, because we can transform the input using nonlinear transformations into nonlinear features, such that using this least squares approach, we can, in closed form solution, also estimate the parameters of, for instance, a polynomial. And that's what's called polynomial curve fitting. So let us now choose a polynomial of order m to model a data set X. This polynomial can be simply written as the sum of these monomials x to the power of j. So we have the sum of m monomials, where the first monomial is just 1, x to the power of 0, then we have x squared, etc. All right, so now we can write this in the same way as before, weight vector transpose x, where now these features have a very specific form. So in this case, the input to the function is still one-dimensional, right? The x is one-dimensional, but the features are computed from this one-dimensional input by simply stacking the monomials into a vector, 1, x1, x2 until xm. And this is how these features look like here. This allows us to express this polynomial curve fitting model using a very simple linear expression. It's linear in W. It's not linear in this input x. Now, as we know, there's two tasks. In training, we want to estimate these parameters w from the dataset x, and during inference, we want to predict y for a novel x given the estimated parameters w. Note that these features here are just one particular choice. They can be anything in practice. They could include, for instance, multi-dimensional inputs, such as images or audio signals. It doesn't need to be a one-dimensional input. Or they can be any other nonlinear transformations of the input, such as radial basis functions, sine and cosine functions, etc. In this particular example of polynomial curve fitting, we're having monomial features. Now, how can we estimate w from the data set x? Well, again, we define an arrow function, a squared arrow function here, which looks the same as before. So we minimize for each data point the sum over all data points, and we minimize the squared errors between the predictions of the model and the observations y. Again, it's important to note that this arrow function is linear in W but not in X. This means with respect to W, we obtain the same problem as before. We have a quadratic problem that has a closed form solution. So we can also write this slightly differently. Here we have the energy again. We can replace this term now with this linear model that we have assumed. And we can also write out linear model or this dot product explicitly in terms of the sum over the elements of W and X. Now we can rewrite this energy function here in matrix vector notation in order to transfer this into the same format as we have used previously, into the same format as the linear regression problem was. How can we do that? Well, if we inspect this equation here, we see that we can choose a matrix X where in each row we stack the monomials. So we have in each column one element of this monomial vector, of this feature vector, 1 x squared until x to the power of m, where m is the degree of the polynomial. And each row is a different data point. That's why I used the subscript I here for the data index. So we have one row for the first data point, one row for the second data point. These are basically the features of the ith data point. Similarly, on the right-hand side here, we can stack all the observations into one single vector. So the first observation, the second observation, and so forth. And then we have the weight vector W. Now, if you formulate this matrix and this vector as such, we see that we have the same formulation as before for the linear regression problem. We can formulate this arrow function, or this energy function here, using a difference between a matrix vector product and the observation vector y. So let's look at some polynomial curve fitting results now. So what I show here are plots of the curve fitted using different degrees m. So here you can see a data set. The ground truth is here in this green thick line, and the noisy observations are in blue. This is what we fit the model to. The polynomial fit is in red, and the test set where we want to evaluate our model is in blue. The test set and the observations are sampled in the same way from this green true underlying model. So here on the left, what we can see is a fit of a polynomial of degree 0, which is simply a constant. You can see that it is not a very good fit to this model. We call this an underfit. It does neither fit the training set, the observations here, neither the test set. On the right, we see a polynomial of degree 1, which is a linear model. It's a line. Again, this is an underfit. It does neither fit the training set nor the test set well. Now, if we increase the order of the polynomial to 3, we get some quite reasonable results for this data set. If we increase further to m equal 9, where we can reduce, m equal 9 means the polynomial has 10 degrees of freedom, because we have this one bias element. This means we can reduce the error to 0, because we can always fit exactly a polynomial with the number of degrees of freedom to a data set with the same number of points. Here we have 10 data points, the green ones. But the fit is actually an overfit. You can see that it oscillates heavily, and while it fits the data points exactly, the training set exactly here in green, predictions for novel predictions for novel points here in blue are not necessarily good. So for instance, here we have huge deviations from the true model. You can see that this red curve deviates and oscillates heavily from this green underlying true model. Now, choosing the correct degree m is a model selection problem. This is called a model selection problem because we have different models, one model for each degree of freedom that we can fit to the data set, but not all of them are equally good. And what we really want in machine learning is we want a model that is good not only on the training set, but also on the test set, because this is where we want to do predictions in the future. So in summary, we want to perform well on new previously unseen inputs, the test set here in blue, not only on the training set in green. This is called generalization, and this separates machine learning from optimization. In optimization, we are just interested in fitting a model to observations. In machine learning, we are always interested in a model that generalizes well. The assumption that we often make in statistical learning theory is that the training and the test data are independent and identically drawn from the data distribution, p data of x and y. All right, this is important because this assures that we can make certain statements about the learning problem. In this case, this data distribution has been chosen as follows. We first sample an x location uniformly between 0 and 1. And then conditioned on this x location, we sample a y location by adding some Gaussian noise. And so we have this sine, this underlying sine curve here, and we add some Gaussian noise with standard deviation sigma to it. Okay. So let's quickly recap the terminology that we're using here. Capacity refers to the complexity of functions, which can be represented by the model. For instance, here we have a too low capacity. Here we have a capacity that's about right, and here we have a capacity that's too high. The model has too many parameters. It overfits the training data, and it doesn't generalize well to the test set. Underfitting refers to models being too simple that do not achieve low error, not even on the training set. This is the case here. And overfitting refers to the scenario where the training error is very small, but the test error, also called the generalization error, is very large. Right? So we want neither of those. We never want a model that's underfitting, nor a model that's overfitting. We want a model that's performing well on the test set, that generalizes well. Here is an example where we can see the generalization error for various polynomial degrees m. Here on the x-axis we visualize, or we plot the degree of the polynomial from 0 to 9. And the model selection problem now is to select the model with the smallest generalization error, or the test error. Here you can see that the training error continuously drops if we increase the degree of the polynomial, which makes sense because we know that for a polynomial of degree 9, we can fit a data set with 10 data points exactly. However, while the generalization or the test error in the beginning decreases, towards the end or after at some degree, it starts increasing again. And this is exactly happening when we start overfitting, right? So the test error goes down, and the training error goes down, and the test error goes up. This is the case for the overfitting case. Here on the left, we have underfitting. Neither of these models or errors are small. Here on the right, we have a very small training error, but a very large test error. And what we want is the best model that produces a small or the smallest generalization error. In general, to choose the best model, we therefore need to split the data set. And the data set is typically split into a training, a validation, and a test set. And we choose the hyperparameters, for instance, the degree of the polynomial, the learning rate in neural networks, etc., using the validation set. It's important to evaluate only once on the test set. And in fact, often the true labels, the true Ys for the test set are often not available. So we cannot evaluate more than once on a test set. And we need to have a model in the first place that's good, which we determine using the validation set. So here's a split of how this, a split that's commonly chosen into 60% training, 20% validation, and 20% test. When the data set is very, very small, we might not have enough examples for splitting the data set further. So we can use techniques such as k-fold cross-validation instead of a fixed split, as shown here. However, in machine learning, often the data sets are very large, and this is not a problem. Okay, so the next thing that we're looking at is called a rich regression. This is a way of also reducing the model complexity, but not by discretely changing the degree or the order of the polynomial, but by adding a regularization term. So we have a continuous parameter that we can tweak. So above, you see the polynomial curve model again. Right? This is this inner product of this weight vector W with the feature with the input x, the features of the input x, where these features are monomials. And on the bottom, we can now see what the ridge regression problem looks like. So this is the error function of the ridge regression problem, where in red, I show the changes with respect to the model that we had before. What changed is that now, in addition to this reconstruction error that we had before, we now have an additional term, which is called a penalty or a regularizer. And that simply tells the model to choose a solution that on one hand fits well, but with some weight, lambda here, that we can choose as a hyperparameter, also makes the weight small, the model weight small, right? And why is it making the model weights, trying to make the model weight small? Well, because in the case where we have this overfitting behavior from before, this typically happens when the weights become very large, where the model fits the training set very well, but is not able to generalize due to these oscillations that we have seen. Now, this is a way of avoiding this. So the idea here really is to discourage large parameters by adding this regularization term with some strength alpha, some strength lambda, that is a hyperparameter that we can choose here. And this problem is also quadratic in W. You can see that on both sides here, we have an expression that's quadratic in W, which means we also have a closed form solution to it. And this is what you can see here at the bottom, again in red, the changes to before. We simply add this lambda times the identity matrix to this xt x term here. How does this look like? So here we have used the same model and dataset from before. This is actually this model with polynomial degree 9, this one here on the right, that heavily overfits without regularization. But now in this case, choosing a mild regularizer, lambda 10 to the power of minus 8, we already get a much better fit than without it. And here on the right, we have chosen a very strong regularizer, where the model basically remains constant 0. So now we have the underfitting situation. So this is here the capacity is about right. Here we have underfitting again. What I visualized here is the model weights with respect to the regularization weight. And again, you can see that if we choose this regularizer very small, we can see that these weights wildly vary, and the magnitude of them is very large. So it becomes ill-conditioned, the problem. And if we increase the regularizer, the weights become smaller. On the right-hand side, you can see a plot similar to the one before, where the training error and the generalization error or test error are plotted over the regularization weight now, not over the degree of the polynomial, but over the regularization weight. And you can see exactly the same behavior. We have an area and a region here where we have overfitting, where the regularization weight is very small. So the training error is very small, but the test error is very large. And then we have this side here where both the training and the test error are large. And we want to choose this point here, which is where the generalization or test error is the smallest, using a validation set. So looking a little bit more general at this problem, we talk about estimators and their bias and variance. What we have seen so far are effectively point estimators. And speaking more abstractly about estimators, we can call a function g an estimator if it maps a dataset x to a set of model parameters w. And we denote this w with a hat here in order to explicitly mark that this is an estimate of this point estimator. It's called a point estimator because given a specific dataset, it gives us one single parameter vector, such as, for instance, using ridge regression, we have a point estimator by executing this equation here. That's a closed form solution for obtaining the parameters. A good estimator is obviously a function that returns a parameter set close to the true one. We assume that this data, the data set that we have drawn is drawn randomly from the underlying data distribution, which means that each element of the data set is independently drawn from this data distribution. Therefore, any function of the data is random, and W hat, this point estimator, is a random variable itself. This means if I choose different data sets from this data distribution, I obtain different estimates. I choose different data sets, let's say with size 10, as we have seen before, but each time I choose a different one from the underlying data distribution, I get a different W. And this leads us to this bias, the terminology of bias and variance, and the so-called bias and variance dilemma. The bias of a point estimator is the expected value of the point estimate over all data sets that I can draw from the data distribution minus the true value of the parameters, the underlying model, the true model, basically. So this is how, in expectation, the point estimator deviates from the true parameters. And this expectation is over all the possible data sets that we can draw from the data distribution. We say that this point estimator is unbiased if the bias is 0. A good estimator has little bias. On the other hand, we have variance. The variance of a point estimator is simply the variance over this estimates W hat over all data sets X. This is just how we can express variance in terms of expectations. And the square root of the variance is often called the standard error. Now, a good estimator not only has little bias, but it also has low variance. Right? So we want to have both bias and variance low. Now, this leads to the so-called bias-variance dilemma. Statistical learning theory tells us, unfortunately, that we can't have both. We can't have an estimator that at the same time has little bias and low variance. There is a trade-off that we have to make. Let's look at a concrete example. This is again the example from before, where in this case, we're fitting a polynomial, now in this case to only 3 data points. And we are fitting it 100 times to 100 data sets composed of 3 points that we each time draw differently from the underlying data distribution. In this case, you can see that the true model is a line. This is this green line. However, we have large variance if we look at these at these estimates to the randomly sampled data points. Right? This is these red lines. Each red line denotes one estimate to one particular triplet of points, one particular data set that we have drawn from the data distribution. And so this is what happens if we choose a ridge regression point estimator with a small regularization weight. With a small regularization weight, we have large variance, so all of these curves are very different. But if we take the mean, this is in black here, the mean of the parameters is simply the mean over this estimated parameters W. We see that the mean model is actually quite a good fit to the ground truth. On the other hand, if we choose a strong regularizer, we obtain less variance in the predictions. You can see that these red lines very much less than before. However, the model has a bias. If we look at the mean, again, of the parameters of these red estimates here, we see that the corresponding model deviates much more strongly here from the true model in green. And this is illustrated here. In fact, this bias variance trade-off can be expressed mathematically. The total error here that we make is exactly equal to the bias plus the variance of the point estimator. So what we want is we want to find the smallest point here. So we want to choose the model complexity such that the total error is minimized. And this is the case when we have this trade-off, this balance between variance and bias. If the model complexity is too low, then we have a strong, large bias, but low variance. If the model complexity is high, we have large variance and low bias. However, it seems it might not be the case in all situations. And that's interesting. For instance, in deep neural networks, the test error decreases with the network width. And there's an interesting blog post I'd like to encourage you to read, which might bring you forward in thinking about this problem more. Okay. Now, in the final part of this unit, we're going to be talking about maximum likelihood estimation. We talk about maximum likelihood estimation as a reinterpretation of the results that we have previously seen by taking a probabilistic standpoint. Let X be a dataset again with samples drawn IID from the data distribution. And let now the model be a parametric family of probability distribution. So here we assume from a probabilistic viewpoint that the model is actually giving us a distribution over outcomes, not a point estimate of y, but a distribution over y's, given the inputs x and the parameters w. And we will see in a bit why we do that. Now, in this case, it is a conditional maximum likelihood estimator because we condition on the inputs x. This conditional maximum likelihood estimator for w is then given as follows. And so this estimate w hat equals, ML means maximum likelihood, equals the maximal value that this model distribution here can take with respect to the parameters w. And y and x here are the data set. So this is again the same notation as before. Y are all the observations and x are all the inputs stacked in rows here. Now, because we assume that this data set has been drawn IID from the data distribution, we can make the IID assumption here, or exploit the IID assumption such that this becomes equal to this here. So we have, instead of the distribution over the joint of all the outcomes, we have now the product over the model distribution of the individual predictions, given an individual input xi, producing an individual prediction yi. Right? So these are individual elements of this data set now. Right? And we can exploit this IID assumption here by replacing this with the product, assuming that all the yi's are, these pairs are independent. Right? So it's a fundamental law of probability, this independence. And then we can simply rewrite this by taking the logarithm of this expression. The logarithm is a monotonic function, so it doesn't change the argmax. Right? And argmax is basically, for the ones who are not familiar with this expression, is basically returning the w that maximizes the expression inside. So we can take the logarithm because it's monotonic. It doesn't change the maximal element, just changes its value, but we're interested only in the element itself. And then because the logarithm of the product is the sum of the individual logarithms, we can pull this logarithm inside here by swapping the product with a sum. And as a result, we obtain what is called the log likelihood. Right? So this is the sum over the logarithm of the model predictions. Okay, so what did we gain? Let's assume for a moment that the model distribution is a Gaussian, where the mean is a linear function of x and w. So it's exactly this linear expression from before, the inner product between w and x, and the variance is sigma. If we now plug this into this maximum likelihood estimation expression from before, we obtain this equation here. This is simply the univariate Gaussian distribution. Now, taking the logarithm here, we obtain this expression. So we obtain the logarithm of this, and the logarithm of this simply cancels with the exponential. Right? So we get this expression here, which remains. Now, the argmax of this expression here is simply the argmax of the right-hand side of this equation, because the left-hand side does not depend on w. It doesn't change with w. It's constant with respect to w. So we obtain, and also we can remove this constant factor here, right? So we obtain this expression. Now, if we replace the argmax with the argmin, we can remove the minus, and we see, again, using the same reasoning as before, that this expression is equal to this expression, which is familiar to us, right? This is the same expression as we have seen before in least squares estimation. So we see that choosing the model distribution as a Gaussian causes the maximum likelihood estimator to yield exactly the same least squares estimator result derived before, again shown here. There's various variations thinkable here. So if we were choosing the model distribution as a Laplace distribution, we would, for instance, obtain not a least squares expression, but a minimizer of the L1 expression. Right? So you can see here the norm, the L2 norm, has been replaced by the L1 norm. Or otherwise, assuming a Gaussian distribution in addition to the Gaussian distribution over the observations, assuming a Gaussian distribution over the parameters w and performing a maximum a posteriori estimation as shown here. So this is simply applying a base rule, right? We have the prior over w, this is a Gaussian, and then we have the Gaussian distribution over these observations here. We obtain a posterior expression, so we obtain the probability of w given y and x. And if you execute this mathematically, you see very quickly that you obtain a ridge regression in this case, right? So there is this connection between maximum likelihood estimation and these linear least squares problems that we've seen before. Now, why is this important? Well, maximum likelihood estimators are actually a very important tool in statistical learning theory, because maximum likelihood estimators under mild assumptions are known to be consistent. This means as the number of training samples approaches infinity, in other words, as n goes to infinity, the maximum likelihood estimator converges to the true parameters. And they are also efficient. What does that mean? Well, it means that this maximum likelihood estimator converges most quickly to these true parameters as n increases. Amongst all estimators, it is the one that converges most quickly. And it provides a nice connection between this probabilistic interpretation, this interpretation using probabilistic distributions for the model, and this least square formulation. And these are the theoretical considerations that make the maximum likelihood estimator so appealing.